Hello, welcome to Attic Academy. Matthew here, and today I will be attempting to teach you the basics of gravity at A2 level. So to start off with, we need a proper definition of what gravity is. So essentially, gravity is the force of attraction that acts and is experienced by any object with mass. So in other words, any two objects that have mass will attempt to pull themselves towards one another, as I'm sure you'll experience every day by walking around on the Earth. So at A2 level you will be required to calculate the force between two objects as opposed to simply calculating the weight of a singular object on Earth. But the question is, of course, how do you go about doing this? Well, thankfully there's a handy little calculation that's already been created for us, which is on the screen now. Now some of you may be a bit confused as to what these symbols actually stand for, so I have created a diagram to explain. So you've got G(mm) over r squared. G is the universal gravitational constant. It's basically a fixed number. There it is now. You may notice it's actually quite small. Now the reason for this is because gravity is, believe it or not, the weakest force in the known universe. In fact, compared to, say, electrostatic force, it's quite frankly pathetic. And a lot of people have trouble grasping this because, of course, we live on a stonking great big ball of rock that sticks us in place all the time. But if you were to hold, say, a fridge magnet over a paperclip, you would notice that, of course, the magnet attracts a paperclip, despite the fact there's an entire planet attempting to pull that paperclip down, whereas the tiny magnetic field created by something as simple as a fridge magnet is enough to lift up the paperclip. As for the M's, big M and little m refer to the two objects in the system. Now you can name them either way round that you feel like, but generally the larger M is dedicated to the larger object because that's logical, whereas R is the separation between the centre of masses of the two objects, sometimes called the radius of the object's orbit. So we end up with the gravitational force of attraction is proportional to the product of the two masses and the inversely proportional to the separation squared, or the radius squared, as it may be. This is the actual technical definition that you will be asked to remember in physics exams. So I'll just run this through with a simple example. Of course, the Earth and the Moon is what springs to mind instantly. So in this example we have to calculate the gravitational force between the Earth and the Moon. So we have the equation here. I've already put out the mass of both the Earth and the Moon and the rough separation of the centre of masses, because of course the orbit of the Moon alters, but that's not important at the moment. So first of all we put in the universal gravitational constant, followed by the two masses of the object, followed by the separation squared, and that will give you the answer of 1.98 times 10 to the power of 20 newtons. So all quite simple, I'm sure you will agree. Moving on to gravitational fields. Now you will be required to remember stuff, just general things about gravitational field for the exam, and one of these things is how to draw them. Now there are two main ways of drawing gravitational fields which I'm going to cover here. First of all, you have equipotentials. Now equipotentials are lines that represent an increase by a set of amount in the field. So in this example I've said 10 newtons. So we have the point mass here, so at, say, this line the force may be 10 newtons, at this one 20, at this one 30, and so on and so forth. You will notice that these lines spread out as you move away from the object in question. This is because, of course, the radius is squared. So as you increase, the rate at which the force decreases also increases. So in other words, as you move out, the size of the force gets smaller quicker. The other way is using field lines. Now these are lines that show the magnitude and direction of the force. The majority of the time you'll be working with a sphere, so the arrows will be of the same size anyway and will all point towards the centre. This is basically the default way of drawing the field. If you're asked to draw a field and it doesn't specify it, this will be the one that you end up drawing. Now, field strength. You'll also be required to calculate the strength of the field at a specific point. So, field strength is a measure of how much force an object would experience per kilogram if it was placed in a specific point in the field. And it can be calculated by using the equation gm over r squared, because what you're essentially doing is removing the little m from the previous equation and replacing it with 1. So yeah, I've just written that there. Finally, the last thing you'll be asked to do with gravity is to calculate gravitational potential. Now, this is where things get a little bit confusing, because in order to measure the potential, we need to have a reference point to measure it from, where the potential is 0. However, gravity is an infinitely reaching force. It will continue to decrease the further you go from an object and the smaller the object gets, but it will never actually reach 0. The only point that will ever occur is at infinity, because then r will equal infinity, and then anything over infinity must equal 0. So we have to use infinity as a reference point. So that's all well and good. So we now have a reference point to measure from, which gives us the following definition. The gravitational potential at a point in a field is the work done per unit mass to move an object from infinity to that point. In other words, it's the work you need to do to push an object into that point in the field from infinity. So, and potential is equal to force times distance. Now, we already have an equation for force. That was gm m over r. So gmm over r squared multiplied by r, we end up simplifying it down to gm over r, because little m is equal to 1 again, because as I mentioned, this is the amount of work we have to do per unit mass, in other words per kilogram, to move something in. So we just use gm over r. Now, there is a bit of a problem though, because gm over r is not correct, as I will hopefully explain with this diagram. So we now have a system, if you like, where infinity is 0 and everything refers back to infinity. So we have the positive running from the object towards infinity. So that direction is positive. Unfortunately, if we were to place the object in the field, it would be attracted to the other object. In other words, the force would be acting in a negative direction. Therefore, the object at that point in the field must have a negative potential, because it intends to go in the same way as the force. So, the calculation for infinity must therefore be negative gm over r. Because also, if you think about it, the potential energy is the work done to move an object from infinity to a point in a field. We do not actually have to do work on that object. It will instinctively want to go towards the other object. So it will always be a negative value. So I thought I'd best explain this with an example. Back to the Earth and Moon example. So simply plug in the values. So we have the mass. So we want to find the potential of the Moon in its orbit around the Earth. So we simply place in the mass of the Earth multiplied by the universal gravitational constant over the radius of the Moon's orbit, and we then end up with this value. So we now have a value for the gravitational potential per kilogram of an object that's in the orbit radius of the Moon. But we want to find the total potential of the Moon itself. So in order to do that, we need to multiply this per kilogram unit by the actual mass of the Moon, like so. And that will give us the total potential energy of the Moon, which is negative 7.62 times 10 to the power 22 joules. So in other words, it's got quite a lot of potential. And, well, that's pretty much it, really. Thank you for watching. If there is anything else you would like us to cover, please leave a comment below, and I hope to see you next time.